Hello, class. Today we're going to discuss Coulomb's law. We have seen that an electric charge exerts a force on either attraction or repulsion. Mr. Coulomb investigated this electric force in the 1780s by using a torsion balance, like in this figure. Since like charges repel, the object on the fiber rope experiences a force and starts to rotate. Here's the equation showing the relationship that Coulomb discovered about electric forces. Q1 stands for the amount of charges on object 1, Q2 is the amount of charge on object 2, and R is the distance between both objects. And then K is a constant, which is 9 times 10 to the 9th newtons times meter squared per coulomb squared. So this equation states that the electric force felt is proportional to the electric charge and inversely proportional to the distance squared. The force is along a line connecting the charges and is attractive if the charges are opposite and repulsive if they are the same. Note that the equal but opposite force on both charged objects. The SI unit for charge is named after coulombs, and we use the letter capital C. In this section, we'll use microcoulombs quite frequently. The charge on one electron has been determined to have a magnitude of about 1.602 times 10 to the negative 19 coulombs, and it's negative. This is the smallest charge observed in nature, and is given by the symbol E. Note that E is a positive number, so the charge on an electron is negative E, and the charge on a proton is positive E. Remember, electrons and protons have the same amount of charge, just opposite signs. Alright, here's our first example. We want to determine the magnitude and direction of the electric force on the electron of a hydrogen atom exerted by a single proton. That is, the atom's nucleus. Assume that the average distance between the revolving electron and the proton is 0.53 times 10 to the negative 10 meters. The first step is to write out Coulomb's law, which is force equals K times Q1 times Q2 all over R squared. Now we just plug and chug. K is the constant of 9 times 10 to the 9th. Q1 and Q2 have the same charge since it's an electron and proton. And the distance is already given in meters. Notice that I didn't bother putting in the negative sign for the electron charge, because I want to calculate the magnitude and use a figure to determine the direction. So the magnitude calculates to be 8.2 times 10 to the negative 8 newtons. And the direction of the electron force on the electric force on the electron is inward, towards the proton, because opposites attract. Alright, next example. Two positive point charges, Q1, which equals 50 microcoulombs, and Q2 equals 1 microcoulomb, are separated by a distance L, which is larger in magnitude, the force that Q1 exerts on Q2 or the force that Q2 exerts on Q1. From Coulomb's law, the force on Q1 exerted by Q2 is this equation down here. And then if we were to calculate the force on Q2 exerted on Q1, it would be the same equation, but the two are flipped, which means that the magnitude is exactly the same. So the equation is symmetric, and with respect to the two charges, so therefore the magnitude of F21 equals the same force as F on 1 by 2, just in opposite directions. Now, to calculate the electric force on a charged particle with multiple charges present, we can apply superposition, meaning, in the example below, which is way harder than what we'll do for this course, but nonetheless, I can use this figure to explain superposition. If we want to calculate the force on charge 3, we can first ignore charge 2 and only focus on charge 3 and charge 1. Now, since opposite attract, force 3-1 is pointed towards Q1. Now, if we ignore charge 1 and only focus on charge 3 and charge 2, the force 3-2 is pointed upward because like charges repel. Now, in this example, to calculate the resultant force on charge 3, we would need to apply vector algebra. However, for this course, we're only going to deal with charges in a straight line. So here's an example. We have 3 charged particles that are arranged in a line. We want to calculate the net electric force on a particle 3 due to the other 2 charges. The net force on particle 3 is a vector sum of force 3-1 exerted on particle 3 by particle 1, and the force 3-2 exerted on 3 by particle 2. So we need to apply Coulomb's law 2 times. One for force 3-1 and the other for force 3-2. First, we'll plug and chug into the force 3-1 and we get 1.2 newtons. Then we plug and chug into force 3-2 and we get 2.7 newtons. Again, notice how I didn't bother with a negative sign yet, because I want to use the figure to determine the direction. So according to force vectors on charge 3, force 3-1 is positive and force 3-2 is negative. Adding 2 vectors together, we get a negative 1.5 newtons. So the charge on 3 is forced to the left with a magnitude of 1.5 newtons.